but came from a condition which was more separate and more organized in the past than at the present time.
That's a strange argument. I mean, I guess I'm not really clear on what he means by the fluctuation. Like, what is the theory is that everything is natural state is to be ordered, and then there was a fluctuation that caused disorder?
No, the natural state is a uniform disorder.
Okay, and then something fluctuated, and so things became ordered.
Right. So we lost the uniformity of disorder, and now we have a pocket of orderliness inside of an enormous system of disorderliness.
Like the little box around the...
Right. So our entire universe with all of its stars and galaxies is this fluctuation within an enormous thing of disorderly uniformity.
Okay, so what is his objection to that?
He's saying that in order to get that in any other system that you might be studying where that happened, you have to borrow orderliness from somewhere else in order to stack it up somewhere. But if you start with uniform disorderliness, you can't really do that. I think that's what he's saying.
Okay. Yeah. It's a strange way to put the argument.
Yeah. Yeah, he says you have to borrow odds to get the thing lopsided, but there's no use borrowing too much.
Yeah.
And I'm not sure why he keeps adding in the Napoleon and the history and the bones and stuff in there. Like, how does a historian who is like pretty sure that in some other book that he may not have looked at yet that the Napoleon or whether will have the same dates, how does that contribute to like orderliness in the past versus more disorder in the future? I couldn't make that connection.
That's what I'm saying. This whole argument is interesting. I don't know.
Yeah.
I'm not really following it.
Yeah. Because, I mean, him adding that...
I understand the main principle, though, but it's just he's putting all this stuff in there that I don't know if he's just trying to be funny.
Yeah, maybe he is making jokes.
Because I think he just trashed the historian.
Yeah.
He's never witnessed anything. He's only making a statement about knowing that probably that date's going to be the same in some other book he hasn't read.
Right, yeah.
That's about all he's doing.
That's right. Yeah. By speaking about the past, he's making a prediction about the future. Yeah.
Yeah.
Okay, so he says, therefore, I think it is necessary to add to the physical laws the hypothesis that in the past, the universe was more ordered in the technical sense than it is today. And I think this is the additional statement that is needed to make sense and to make an understanding of the irreversibility. That statement itself is, of course, lopsided in time. It says that something about the past is different from the future. But it comes outside the province of what we ordinarily call physical laws because we try today to distinguish between the statement of the physical laws which govern the rules by which the universe develops and the law which states the condition that the world was in the past. This is considered to be astronomical history. Perhaps someday it will also be part of physical law.
All right.
So that's interesting. Because he's right. He like the previous chapter when we were talking about symmetry, he was talking about symmetry of time. And then he had to make the caveat that like, well, of course, this excludes something like the Big Bang.
Right. Yeah.
And now he's talking about this also doesn't work when it doesn't work in terms of physical laws and symmetry, but astronomical history, he's saying, is basically a different thing. In other words, if you go back in time, the universe changes. It doesn't look the same as it does today.
Right.
So there isn't a symmetry there, but that's astronomical history. It's not about fundamental laws.
Yeah.
Okay. So now he goes through a whole description of he's trying to show something, and he's basically talking about a machine, an imaginary machine that can only turn one way. It's basically like a sawtooth ratchet powered by gas. by Brownian motion of gas molecules. And if you make it so that the ratchet can only turn in one direction, that the irregular impacts of the gas molecules hitting the little fan blades will result in the thing only being able to ratchet over in one direction because the ratchet keeps it from going the other way. But he just explains that if you give it enough time, everything heats up and then eventually it'll just go in both directions and basically effectively stop moving.
Right.
But yeah, you could start out and be like, look, I've built a perpetual motion machine. It'll only turn in one direction. It'll keep doing it. But technically speaking, it'll heat up, and then it stops working.
Yeah. So you have to maintain it all the time.
Right. Okay, so he says the conservation of energy would let us think that we have as much energy as we want. Nature never loses or gains energy. Yet the energy of the sea, for example, the thermal motion of all the atoms in the sea, is practically unavailable to us. In order to get that energy organized and herded and make it available for use, we have to have a difference in temperature, or else we shall find that although the energy is there, we cannot make use of it. There is a great difference between energy and availability of energy. The energy of the sea is a large amount, but it is not available to us.
I think this is a great point.
Yes. The conservation of energy means that the total energy in the world, and I think he just means in the universe, is kept the same. But in the irregular jigglings that energy can be spread around so uniformly that, in certain circumstances, there is no way to make more go one way than the other. There is no way to control it. I think that by an analogy, I can give some idea of the difficulty in this way. I do not know if you have ever had the experience, I have, of sitting on the beach with several towels, and suddenly a tremendous downpour comes, and you pick up the towels as quickly as you can and you run into the bathhouse. Then you start to dry yourself, and you find that this towel is a little wet, but it is drier than you are. And you keep drying with this one until you find that it is too wet. It is wetting you as much as drying you. Then you try another one, and pretty soon you discover a horrible thing that all the towels are as damp. Are damp, and so are you. There is no way to get any drier, even though you have many towels, because there is no difference in some sense between the wetness of the towels and the wetness of yourself. I could invent a kind of quantity which I could call ease of removing water. The towel has the same ease of removing water from it as you have. So when you touch yourself with the towel, as much water comes off the towel onto you as comes from you onto the towel. It does not mean that there is the same amount of water in the towel as there is on you. A big towel will have more water in it than a little towel, but they have the same dampness. And when things get to the same dampness, then there is nothing you can do any longer. Like, I love that. I could just picture him trying to dry off and coming to this realization that he isn't going to get any drier with this collection of towels. And then working it out in his mind about uniform dampness.
It's a good analogy, though. It's like that's why I like to think of the, we say the potential, in an electric current or whatever. And so you think of the difference. You got to have this difference in potential.
In a very wet person and a very dry towel, there's a lot of potential.
Yeah, you can have all this. You can have all this energy, but if you and the energy or the thing that what you're trying to do with the energy, you need the difference into potential to get it to go in a direction.
You need it to move
in
one
this
way,
orderly direction, so that you can turn something.
Right.
Well, if there's just as much energy on the other side, then there's potential energy, then it won't really go anywhere.
Right.
It might move back and forth a little bit.
Yeah.
So the big issue is finding the energy that's a whole lot in one place and none in the other, or very little in the other place.
Right. Or just very little of the kind you're trying to move.
Right.
Yeah. I just love that it's about towels.
Yeah, it's great.
Yeah. Yes, between you getting right after you get out of the shower and a very dry towel, there's a lot of potential.
Yeah. The water just
just
moving
move
right
off off of you and directly onto the towel, and you basically can get dry. But if the towel was in the shower with you, there's no chance that it's going to move from you and onto the towel. It'll be an equal exchange. So he says, now the water is like the energy because the total amount of water is not changing. If the bathhouse door is open and you can run into the sun and get dried out or find another towel, then you're saved. But suppose everything is closed and you can't get away from these towels or get any new towels. In the same way, if you imagine a part of the world that is closed and wait long enough, in the accidents of the world, the energy, like the water, will be distributed all over the parts evenly until there is nothing left of one wayness. nothing left of the real interest of the world as we experience it. So thus, in the example of the ratchet, which is a limited one in which nothing else is involved, the temperatures gradually become equal on both sides, and the wheel does not go around either one way or the other. In the same way, the situation is that if you leave any system long enough, it gets the energy thoroughly mixed up in it, and no more energy is really available to do anything. Incidentally, the thing that corresponds to the dampness or ease of removing water is called the temperature. And although I say when two things are at the same temperature, things get balanced, it does not mean they have the same energy in them. It just means that it is just as easy to pick energy off of one as to pick it off of the other. Temperature is like the ease of removing energy. So if you sit them next to each other, nothing apparently happens. They pass energy back and forth equally, but the net result is nothing. So when things have become all of the same temperature, there is no more energy available to do anything. The principle of irreversibility is that if things are at different temperatures and are left to themselves, as time goes on, they become more and more at the same temperature, and the availability of energy is perpetually decreasing. This is another name for what is called the entropy law, which says that entropy is always increasing. But never mind the words. Stated the other way, the availability of energy is always decreasing. And that is a characteristic of the world in the sense that it is due to the chaos of molecular irregular motions. Things of different temperature, if left to themselves, tend to become of the same temperature. If you have two things at the same temperature, like water on an ordinary stove without a fire under it, the water is not going to freeze and the stove is not going to get hot. But if you have a hot stove with ice, it goes the other way. So the one-wayness is always to the loss of the availability of energy.
Yeah. That's great.
It would be cool to have a stove, but like you put water on it, turn it on, and it freezes the ice.
It freezes the water.
It freezes the water, and the stove gets hot. It just pulls the heat out of it. So he says, that is all I want to say on the subject, but I want to make a few remarks about some characteristics. Here we have an example which is an obvious effect, the irreversibility. It is not an obvious consequence of the laws, but is in fact rather far from the basic laws. It takes a lot of analysis to understand the reason for it. The effect is of first importance in the economy of the world, in the real behavior of the world, in all obvious things. My memory, my characteristics, the difference between past and future are completely involved in this, and yet the understanding of it is not available by knowing about the laws. It takes a lot of analysis. It is often the case that the laws of physics do not have an obvious direct relevance to experience, but that they are abstract from experience to varying degrees. In this particular case, the fact that the laws are reversible, although the phenomena are not, is an example. Yeah. Is it break time?
Yep.
Probably should take a break, yeah.
All right. We'll be right back.
It's not reversible.
Snakes!
Can't go back.
In the beginning of the history of experimental observation or any other kind of observation on scientific things, it's intuition, which is really based on just experience with everyday objects that suggests reasonable explanations for things. But as we try to widen and make more consistent our description of what we see, as it gets wider and wider and we see a greater range of phenomena, the explanations become what we call laws instead of simple explanations. But the one important odd characteristic is that they often seem to become more and more unreasonable, and more intuitively far from obvious.
Trying to make, what is it? Maca everything and other stuff. Maca everything and other stuff over here, Brothers of the Serpent podcast. A joke that didn't get made on the last show.
That's right.
I had to bring it up. Cheery everything.
Yes. Your favorite breakfast cereal.
You just need a Cheerio particle. I think that's what they were saying in the Discord. Cheerio particles.
Macker everything and other stuff.
Yeah. Yeah.
Because you can't actually, they won't all be macaronis.
yeah.
And cheese
And
is not really.
Yeah, right. It's just going to be maca everything and other stuff.